Alrighty, lads and ladies, welcome back to pre-calculus. Today we are going to start talking about, properties of logarithms. And after that, we're going to talk about some logarithm equations. So today is going to be an interesting day. I guess not really logarithm equations, I should correct that. We're going to talk about exponential equations, which we solve using logarithms. And then we will almost be ready for exam 3. So I'm going to give you a little bit of a roadmap where we're going for the rest of the term here at the start of class, and then we'll dive in. I know everybody is anxious to get their tests back. I am almost done grading your tests. I just have a few more left to do, and they will be up by later in the day today. I know it's taken quite a long time. I apologize for that. But just the format, doing tests this way with the option to do them at the testing center or online, and then at the original day or the makeup day, I end up having to grade 4 different tests, so it takes a lot longer. But they are coming, I promise you that. Here we go. So this is MAC1140, section 009, which is pre-calc. And today is the 9th of November, 2021. Today, we'll talk about laws for logarithms, or laws of logarithms, your book calls them, which is section 4.4. And we're going to start on exponential and log equations. Oh, sorry, this is 4.5. And this is 4.6. Before we get into that, though, I do want to talk a little bit about the next test, because we're already almost there. And complicating factor. So the college is closed. This Thursday. For Veterans Day. And that's nice. But it does mean that we're losing a day kind of at the end of the term here as we get close to Thanksgiving, where we're already going to lose time. It's really not the best thing for us schedule-wise. What I'm going to do, I will record a lecture for Thursday. And post it to Canvas. I'll upload it to YouTube and post to Canvas. Because we really can't afford to burn any more time. So it might not feel like it, but we're actually pretty close to the end of the term. I think our last day of class is Thursday, November 2nd. Let me pull up your syllabus and triple check that. I believe that's the case. Yeah. So here's kind of the roadmap from here. We will have our test on logarithms and exponentials on the 18th, which is a couple weeks after when we wanted to have it. And it's okay, we put a little bit more time into the stuff at the start of the semester. That means we're going to be talking about matrices and the algebra of matrices, systems of equations for the remaining 2 weeks of class. We'll be able to talk a bit about partial fractions and sequences in series. That's not bad. We definitely, this is way more time than we need for that. What is going to happen is probably we're going to squeeze conics out. So the last week is normally spent talking about conic sections, and we're not going to have time to do that. I will slim down the matrix algebra sections to just the bare necessities, but that's where we're going to go. So because we're a little bit behind in the schedule, not the end of the world, we really can't afford to sacrifice an extra day here. So I'm going to record and post a lecture for Thursday, and the exam 3, will be the following Thursday. which is the 18th. And that exam will just cover logarithms, exponentials, the properties, and the associated equations. Then whatever time is left in the semester, we will spend learning about systems of equations, matrices, and matrix algebra. The only other material besides those things, systems, matrices, and matrix algebra, that I really feel is necessary for us to cover in this class is sequences and series. I need to introduce you guys to that notation. We may end up doing that in something like a worksheet if we're really crunched for time at the end. We'll see how it goes. But that's sort of the roadmap for the rest of the term. So exam 3 is going to be Thursday, next Thursday, right? Not this upcoming Thursday, but the Thursday after that. And then the remaining portion of the course will be on linear algebra, systems and matrices, and sequences and series. All right, with all that said, let's dive into the material for today. So laws of logarithms. Each of the rules for exponents that we talked about at the start of this chapter 4 has a corresponding law or rule for logarithms. And you deduce the rules for logarithms just by thinking of them as the inverses of exponential functions. So you may remember, for example, that if you have a to the x times a to the y, two exponentials multiplying with the same base, that is the same as a to the x plus y. Well, if you rewrite this as a statement about logarithms, see, this says that multiplication outside on exponentials is the same as addition inside. And since the base A logarithm is the inverse of the base A exponential, that means that the base A log of x times y, multiplication inside, is the same as the base A log of x plus the base A log of y, addition outside. We also had a rule that said a to the x divided by a to the y is the same as a to the x minus y. The corresponding rule for logarithms. So this says division outside is subtraction inside. And since the base A log is the inverse, that means that division inside a logarithm is the same as subtraction outside. So the base A log of x over y is the base A log of x minus the base A log of y. And then the last one, and perhaps the most useful for us when it comes to interpreting as logarithms, says that if you take a power and you raise that to the power a to the x all to the y, that's the same as a to the x times y. So powers outside become multiples inside. What that means for logarithms is that powers inside the base a log of x to the y become multiples outside. So these are your three kind of primary laws for logarithms. I want to get us some practice just using these. We can use them to sometimes evaluate expressions that would otherwise be tricky to evaluate. We can also use them to expand and contract statements about logarithms to make them easier to work with. So maybe I'll label these as 1, 2, and 3. First things first. Let's practice just evaluating some expressions. by using the log laws. And we'll start with something like the base 4 log of 2 plus the base 4 log of 32. And then maybe the base 2 log of 80 minus the base 2 log of 5. And the last one your book has here, I don't know why they shoved this particular example here. It's not a particularly appropriate one, but you want to evaluate negative 1/3 times the base 10 log, common log of 8. So the trick to each of these is to apply one of those log laws to rewrite it as something that we can come up with a little bit easier. The first one, really, you could figure out each of these things individually, like the base 4 log of 2 and the base 4 log of 32. They're not integers, but you can ask yourself what power of 4 is equal to 2? That's 1/2. 4 to the 1/2 is 2. What power of 4 is equal to 32? That's not as obvious. It turns out to be 5/2. But you could get there if you think about it carefully enough. But it's much easier, and this is one of the really powerful things about these logarithm laws. It's much easier if you combine these using that first rule before trying to evaluate either piece. So if I apply that very first logarithm law here, that says the base A log of one thing plus the base A log of some other thing is the base A log of the product, I get log base 4 of 2 times 32. Right? Multiplication inside is the same as addition outside. And 2 times 32 is 64. So this is the base 4 log of 64. And that we should be able to think of pretty readily without any sort of weirdness. So how do we figure out what the base 4 log of 64 is? What's the question we should be asking ourselves?
4 raised to what power is 64?
Very good. Yep, what we want to ask, what 4 raised to what power is equal to 64? Well, what is that? 4 raised to what power is 64?
3.
Very good, right? 4 times 4 is 16, times 4 again is 64. So 4 to the 3 is 64. So we combine using that first rule, and then we just think about the definition of the logarithm. We get a nice integer out. All right, what about the second one here? How do I rewrite log base 2 of 80 minus log base 2 of 5 as a single logarithm?
Log base 2 80 over 5.
Very good. And everybody heard what Jalen said, right? It's the log base 2 of 80 over 5. This is not log base 2 of 80 over log base 2 of 5. These are totally different animals. So it's one logarithm with the ratio inside, not the ratio of logarithms. This wouldn't help at all because I still have to figure out the base 2 log of 80 and the base 2 log of 5. What's worse, though, is that it's just not true. These are not equal to each other, but this is equal to this difference. Now, 80 over 5, what is that?
$16.
Very good. And what's the base 2 log of 16? 2 to what power is 16?
4.
Very good. 2 to the 4 is 16. So the base 2 log of 16 is 4. All right, this last one is a little bit unnatural in the sense that that we're not going to get a nice number out, but I'll show you how to what they're looking for here and then how to calculate it. So first, I have a constant out front of my logarithm. And by our third log law, that constant can come inside. That's the same thing as having the log of 8 to the negative 1/3 power. And then like we did in the previous two examples here, I want to simplify the inside in hopes that I can come up with a nice value. What is 8 to the negative 1/3? That's kind of a lot to do at once, right? So whatever it is, it's got to be 1 over 8 to the positive 1/3, right? That negative power moves me downstairs. And then what is 8 to the 1/3? The cube root of 8. What is that?
2.
Yeah, good. So this is the log, or the base 10 log of 1 over 2. Now, 1/2 is not a nice power of 10. So unlike these last two, where we can figure this out just by thinking about the definition, this guy, unfortunately, I can't find a TI-30 emulator, so I'm going to use my TI-84 emulator. But you have the same buttons I do here. So you've got an log button on your TI-30. You would type log of 1 divided by 2. And I recommend closing the parentheses. Use good syntax. So this is what we want, the log of 1/2. That's what we type, log of 1/2. And it gives us negative 0.301-ish. I'll put an approximate, negative 0.301. All right. There are plenty of problems where you will need a calculator. Anytime you're trying to evaluate a logarithm where the inside is not a clean power of the base, you'll end up needing to use a calculator. Your calculator only has these two buttons though, right? The log and the ln button. If you need to evaluate some other base logarithm, the tool for doing that is called the change of base formula. So to evaluate the log base b of x, where x is not a nice power of b, we use the change of base formula. And this formula looks a little bit intimidating at first, but I'll do my best to explain it in a way that makes it tractable. What it says is that if you start with the log base b of x, right, the thing that we want to figure out, where b and x are both known numbers, like the log base 10 of 1/2 or whatever, you can rewrite this as any other base logarithm. I can rewrite this as the log base c of x over the log base c of b. So it's the log with your preferred base of the inside divided by the log with your preferred base of the old base, where you get to choose c. Choose any number or any base c as long as it's greater than 0. All right, remember bases for logarithms, just like exponentials, have to be positive. So this is the formula. And I want to show you kind of two special cases of this, which we use when we want to put things into our calculator. The first special case is if you take c to be 10. So you want to change some other base logarithm into a common log. This says then that the base b log of x is the base 10 log of x, or just log of x, divided by the base 10 log of b, your old base. The other one, where you take c to be the number e. So you're going to change your whatever base logarithm into a natural log. And here that says the base b log of x is the ln of x over the ln of b. And mostly it's the far bottom right one that we use. Usually if I need to evaluate like the base 7 log of 12 or something, I would write that as the ln of 12 over the ln of 7, right? And just plug those into my calculator. We'll get some more practice with this in a second. Before we do that, I want to look at kind of the other way you can use those log laws.
I'm sorry, can you put it back so I can take a picture of the?
Yeah, of course. Here we go. A little faster. There we go.
Thank you.
Of course. All right. So let's practice kind of expanding and combining logarithms. I'm going to expand each of these as far as we can. I've got the base 2 log of 6x, the base 5 log of something like x cubed times y to the 7, the natural log of a times b over the cube root of c. And I'm going to add one more in here. Let's do the natural log of x y squared over, say, z times the square root of a, something like this. All right. So let's start at the top. If I want to expand this out as much as possible using my laws for logarithms, what do you see going on inside here that I could use one of those laws on?
Log 2 of 6 plus log 2 of f.
Yeah, exactly. So I have some multiplication going on inside, which I can turn into some addition going on outside. So this would be the log base 2 of 6 plus the log base 2 of x. All right, multiplication inside, addition outside. In part B, I've also got some multiplication going on inside. I also have some powers. So which should I do first? Should I split up, turning the multiplication inside to addition outside? Or should I try to bring the powers down first? What do you think?
Bring the powers down.
I am. If these were both raised to the 3 or both raised to the 7, if everything inside was raised to the same power, then I could bring the powers down first. But what you notice here is that it's only the x being raised to the 3, and it's only the y being raised to the 7. So which one would I bring down? Would I bring down a 3 or a 7 or both? If I brought down both, like 3 times 7, that would mean x times y is all being raised to the 21. And that's not quite what we have here. So what we need to do is first split it up. I need to get a log of this thing plus a log of this thing, and then bring the powers down. So I would first write this as the base 5 log of x cubed. And don't feel bad. The reason I asked that question is because nearly everybody makes that mistake at first. First write this as the base 5 log of x cubed plus the base 5 log of y to the 7. It's kind of thinking about the order of operations backwards almost, right? So kind of what's the outermost thing going on? We want to start with the outermost thing. And the outermost thing going on in here is this multiplication. But now that I have a log of x cubed and a log of y to the 7, each of these insides is being raised to this power. So now I can bring those powers down. So this 3 will come down, and I'll have 3 times the base 5 log of x plus this power can come down, and I'll have 7 times the base 5 log of y. So originally only the x had the cube. So in the expanded version, only the x term should have a 3. And originally only the y had the 7. So in the expanded form, only the y term should have a 7. If we apply that same sort of logic to part C, where within the logarithm, I look for the outermost operation and sort of expand that out first, here, sort of that outermost operation is this division. So I would want to begin part C by writing this as the ln of AB minus the ln of the cube root of C. Now, in this first piece, I have an ln with a product inside, so I can write that as the ln of A plus the ln of B. And this last guy, the cube root of C, the ln of that, that's the ln of C to the 1/3. Right? Because the cube root is the same as a 1/3 power. So this is going to be the ln of A plus the ln of B minus 1/3 times the ln of C. Kind of makes sense here. Any questions on these first few guys? Okay. For the last fella here, again, we want to apply that same sort of logic where I expand out thinking about the outermost operation inside the log first. So I'd start here by writing this as the ln of x times y squared minus the ln of z times the square root of a. And I'll write the square root of a as a to the 1/2 in this step. Now, each of these two pieces has some multiplication going on inside. So I can expand each of them. The first one would be the ln of x plus the ln of y squared. When I go to expand the second piece, there's something I need to be very careful about. See, this negative here really belongs to anything that comes from this term. Both of those original pieces are downstairs. It's one way to think of it. So in the expanded form, both of the associated pieces should be negative. The piece that comes from the z here should be negative, and the piece that comes from the root a here should be negative in the expanded form. If I'm just being algebra teacher, I would say you're replacing this single quantity by a sum of two quantities. And anytime you do that, you need to do so in parentheses. So I would open up a big parentheses here and say that this is the ln of z plus the ln of a to the 1/2. And then that whole thing needs to go in parentheses.
Yeah,
This.
and there's no
Okay,
yoga today. There's no yoga today.
What?
No yoga today.
Now we will distribute this negative and also pull down the 2 powers. So this is the natural log of x plus 2 times the natural log of y minus the natural log of z minus 1/2 times the natural log of a. And the most common mistake I see on any of these sorts of problems is giving me this term with a plus rather than a minus, because we just want to rewrite this as ln z plus ln a to the 1/2. But we forget that we're replacing this single term by 2 terms, which means the negative out front really needs to be distributed to both of those terms. So when you solve problems like this, please be mindful that in the fully expanded version, any term that originates from a piece downstairs should be negative in the expanded version. So both the z and the root a were downstairs inside the log. That means that in the expanded version, both the z piece and the root a piece should be negative. All right, any questions on any of these examples? Of course, you can run this in the other direction also. I could give you any of the answers from that last example and say combine these into a single logarithm. So let's take a look at that. Obviously, I don't want to do those exact examples, so we'll say combine into a single logarithm. We'll just look at a couple things here, something like 3 times the log of x plus 1/2 times the log of x plus 1. And 3 times the ln of z plus 1/2 times the ln of t minus 4 times the ln of t squared plus 1. So looking at this first piece here, if I want to run the steps that I was doing in the previous example in exactly the backwards order, what would be the first thing I do?
Put 3, 1/2, and 4 into the power.
Very good. So I want to take, normally my last step when I'm expanding is to bring the powers down. So my first step when I'm combining should be to bring these powers inside. Right, bring these multiples inside as powers. So this would be the log of x cubed plus the log of parentheses x plus 1 to the 1/2 power. And now that I just have straight up log of something plus log of something else with no numbers out front, now and only now can I combine those into a single log. So this would be the log of x cubed times x plus 1 to the 1/2, which I'll write as the square root of x plus 1. And that's it. Now I have a single logarithm. We'll do the same thing in part B. I begin by bringing all of the powers in, all these multiples out front inside as powers. That'll give me the ln of z cubed plus the ln of t to the 1/2 minus the ln of, and this is another place we need to be careful with parentheses. I'm bringing this 4 inside as a power. That means everything inside that logarithm is going to get that power. So we need to write this as parentheses t squared plus 1 all to the 4. Now the first two pieces I can combine as the ln of z cubed times t to the 1/2 is square root of t. And then I still have my minus ln of parentheses t squared plus 1 to the 4. And you notice I'm really only doing like one thing at a time, right? I'm not trying to mash all of this together into a single logarithm in one step. Break it down, bring the powers in. Okay, good. Then combine these 2 at a time, not trying to do everything all at once. This way, you're much less likely to make mistakes. And also, as I'm grading your work, I can give you more credit for the steps you get correct, even if you make a mistake in one of the later steps. So by splitting it up into multiple steps, you both kind of help your brain organize your thoughts a little bit better. And you also make it easier for your reader, or in this case, your grader, me, to tell what's going on and what you're doing and where you're comfy in. All right. Any questions on either of these guys? Feeling good? Okay. So the new homework for this week, I'm publishing one homework set for you guys today that is due next Tuesday. It has a bunch of 4.4 and 4.5 stuff. 4.4 is all the stuff that we just did, right? Expanding and combining logarithm expressions, sometimes using those rules to help you evaluate a logarithm that is otherwise tricky to evaluate. The next section has to do with solving equations. And I want to look at a handful of those equations with you now. We are finally ready to solve the equation that sort of started this whole mess. This is exponential and log equations, which is section 4.5. All this stuff began, all this log stuff, by thinking about the equation 2 to the x equals 3. We can solve this now. So if I start with 2 to the x equals 3, I want to think of an operation I could do to both sides that will get rid of the, how should I say this, that will bring the x down out of this power. Instead of having like 2 to the x, I would like to just have x itself.
Log 2 over 3 equal to x.
Yeah, very good. So what we're going to do is we're going to take logs on both sides. This is one of 2 new operations that are going to be introduced in section 4.5. the first new operation is taking logarithms on both sides. It's the same idea as like squaring both sides or taking the square root of both sides. We're not going to multiply or divide by something. We're going to plug both sides into a certain function. Here, since I have a base 2 exponential, the first thought would probably be to take a base 2 logarithm. So I get the base 2 log of 2 to the x is equal to the base 2 log of 3. And then using a property that we actually discussed last time, what is the base 2 log of 2 to the x?
X.
Yeah, it's just x, right? The base a log of a to the x, because these are inverse functions, just gives you x. So you get here x is the base 2 log of 3. And if I wanted to put this into my calculator, I would use the change of base formula to rewrite it as the ln of 3 over the ln of 2. And that, you will see, will be that number that I was giving you guys on our first day of playing with this stuff, the ln of 3, close the parentheses, then divide by the ln of 2, close the parentheses, enter. That's that 1.58496.
What would be if you use log of 3 by log of 2 instead?
You could, you get the same thing. So the change of base formula allows you to convert any log into either a natural log or a common log, and you'll get precisely the same thing. Now, I chose to use the natural log here for a reason. It's because generally when we solve equations like this, and this was going to be my next comment, generally, we just take the ln of both sides. Right, remember we said that the base e exponential is the only exponential anybody ever wants to deal with. In the same way, the natural log is really the only log anybody ever wants to deal with. And because when we arrive here using the base 2 log, in order to get a decimal approximation to that answer, I need to convert into either the natural log or the base 10 log. It's nicer to just start with this in the first place. So I could have said, okay, I'm starting with 2 to the x equals 3, and I'm going to take logs. But specifically, I'm going to take the natural log on both sides. So I get the natural log of 2 to the x equals the natural log of 3. This doesn't clean up as immediately as taking the base 2 log does, but it does get us to this form of the answer right away, which is nice because this is easier to punch into a calculator or a computer if you have to. Also, everybody loves ln, right? It's just the better function. The downside of using the natural log instead of the base 2 log is that the natural log of 2 to the x is not just x. But using the properties that we've learned today, I can bring this x down from the power in front of the natural log where it becomes a multiple. So I get x times the natural log of 2 is equal to the natural log of 3. And don't be intimidated by this. X times the natural log of 2. The natural log of 2 is just a number. It's like 0.69, right? It's just a number. So my final step here would be to divide both sides by the natural log of 2, getting me x equals natural log of 3 over the natural log of 2, as we did before. This is the exact answer, right? You could call either of these, the base 2 log of 3 or ln 3 over ln 2, the exact answer. And there's really no nicer way to write it. It's not a rational number. You can't express it cleanly in terms of ratios of integers or anything like that. This decimal 1.58496 blah, 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 that's an approximation. So if you're told to give the exact answer, we want one of these. You could write it either way. If you're asked for a decimal approximation, then you put it into your calculator and you get this out and you round wherever they tell you to round. All right. So most exponential equations will eventually reduce to something like this. Sometimes you have to do some more algebra ahead of time, but the kind of general procedure for solving exponential equations, which are equations where the variable is in the exponent. First, you want to isolate the exponential. Like 2 to the x is the exponential term here, so I isolate him, get him alone. Then you take logarithms. It's up to you. You can take the ln of both sides or the log of both sides. You can use any base logarithm you want. As I solve these, I'll always use the natural log, the ln, because it's just the nicest of all base logarithms. And then you solve the resulting equation. Taking the logarithms, this is the nice part. This gets the variable out of the power. So kind of built into step 2 there is using this exponent rule or this logarithm law to get the variable down out of the power where you can then solve for it. So nothing crazy. You do need to remember to first isolate the exponential term. Right? If you don't do that, then it's possible to make mistakes. It's not that it's impossible to solve these equations without doing that first. It's just that it's much nicer if you do that first. So let me look at a few examples. So first, let's solve equation 3 to the x plus 2 equals 7. 7 is not a nice power of 3. Right? If this was a 9, then I could say, okay, 3 to the x plus 2 equals 3 squared. So x plus 2 equals 2, and x has to be 0. But most of the time, this number will not be a nice power of this number. And the only way to proceed then is using logarithms. So we'll start by taking logs.
Sorry to interrupt you, but someone asked if they could take a picture of the procedures.
Oh, sure. Yeah, I missed that. I apologize. Right. So first we isolate the exponential term. Then we take logarithms and apply whatever log rule we need to get that variable down out of the power. And then we solve the resulting equation. Yeah, of course, no problem. Okay. So coming back here, my exponential is the 3 to the x plus 2. So that's already isolated. There's nothing like multiplying over here or adding over here. I've just got my exponential equals some constant. So my first step would be to take logs, and I'll use the natural log. Then, according to that rule for logarithms, this power, the x plus 2, can come down in front. And that will give me x plus 2, and it's important we write it in parentheses because again, it's like a single chunk that's coming down here. X plus 2 times the ln of 3 equals the ln of 7. And I want to get x alone. There's a couple things in my way. There's this ln of 3 that's multiplying x plus 2 in my way. And then there's the plus 2 in my way. I can first divide over by the natural log of 3, and that will get me x plus 2 equals ln of 7 over ln of 3. And then I can subtract 2 from both sides. So I get x equals the ln of 7 over the ln of 3 minus 2. And this is what we would call the exact solution. But it is definitely true that sometimes you want to know about how big is this, right? Is this like 5 or like 20 or negative 2 million? It's not super obvious. So we can put it into our calculator and see about how big it is. So that's the ln of 7 divided by the ln of 3. And then subtract from that 2. We get about negative 0.228756. Call that negative 0.229. And this, of course, is an approximate solution. So nothing too bad here. I'm going to show you a few more examples where the algebra steps that lead up to it are slightly more complicated, and we'll just work our way up. But the basic idea is the same. Isolate the exponential term, take logarithms, apply the log properties to get the variables down out of the power, and then solve for that variable like you would in any other equation. So let's solve 8e to the 2x equals 20. Is there anything I should do here before taking logarithms?
You can divide both sides by 8.
Yeah, very good. I don't have my exponential alone. And while it is possible to take the ln of both sides here, you would have to be very careful in how you handle the left-hand side. So the smarter move is to isolate the exponential first, as described in the procedures. So if I divide both sides by 8, I get e to the 2x equals 20 over 8. And 20 and 8 are both multiples of 4. So that's the same as saying e to the 2x is equal to 5/2. Now I take logs. And I get the ln of e to the 2x is equal to the ln of 5/2. What is the ln of e to the 2x?
2x.
Good, it's just 2x. You could write it as 2x, bring this down, times the natural log of e, but the natural log of e is just 1. So it's nice to do those in a single step, right? The ln of e to some stuff will always just be that stuff. So what we get here is 2x equals the natural log of 5/2. And again, this is a linear equation. We can solve this just by dividing both sides by 2. So I get x equals the ln of 5/2 all divided by 2, which I could also write as 1/2 times the ln of 5/2. Same thing. Question. Is this the same as the ln of 5/4? Can this 2 come inside? Can I multiply those fractions, or can I divide these?
No.
Yeah, no, this is not the same. If you're ever wondering, you can check, right? It's the beauty of calculators is that they allow you to check your exact answers. So if I take the natural log of 5/2 and then I divide by 2, that's that first form. So this guy, according to my calculator, is about 0.4581. If I'm insecure about this step, I could check him and ask, okay, is the ln of 5 divided by 2 times 1/2 the same? And yeah, it is. This is also 0.4581. And if I want to know, okay, I know this is the correct answer and it has this decimal, which is the same as this answer. So this also must be correct because it has the same decimal. What about the last guy? Is that the same as the ln of 5 divided by 4? No, he's like 0.2231. So this is definitely not correct. The moral of the story here is when it comes to manipulating logarithm expressions, only do the things that you know for sure are correct, right? The only things we can do to logarithms are exactly the things we've described in those properties and rules. Anything else probably isn't kosher, probably won't be correct. It can be tempting sometimes. There are a lot of ways to misinterpret the log laws. And there are a lot of ways that our brains, when we look at the notation, kind of want to treat things a certain way, whether those things are correct or not. You should always double check your work. And one easy way to do that is to just, find the decimal approximation for any forms of the answer that you think are correct and verify that, maybe I want to give my answer like this. If I'm not sure if this is correct, I can check that they have the same decimal value. If I'm tempted to do something like this, I can check and see, oh, it has a different decimal value. Must not be correct. Okay. This is sort of the gentlest form of how I can change an exponential from the straight up like a to the x equals b thing. But there are many other ways. Get some more paper and we'll look at some more complicated examples of exponential equations. This next one's a lot of fun. Let's try to solve 3x e to the x plus x squared e to the x equals 0. So I've got a bunch of stuff on one side. The right-hand side is 0. But there's no obvious way to isolate this exponential. Does anybody have any ideas what we could do with this left-hand side here?
Can you put e to the power of x and 3x plus x squared?
Very good. I have a common factor of e to the x. So let me factor e to the x out. What would be left then is 3x plus x squared. So I have 3x plus x squared times e to the x equals 0. And this factors. And the 3x plus x squared also factors. I can factor that as x times 3 plus x times e to the x equals 0. And just like with a polynomial, once you have a bunch of factors all equal to 0, you can set each of the factors equal to 0 on its own. In other words, the only way to have a bunch of things multiplying to get 0 is if at least one of them is 0. So one solution will come from setting x equal to 0 on its own. Another solution will come from setting 3 plus x equal to 0, which means x is -3. And then a possible third solution would come from setting e to the x.
But is it possible to e to the x be 0?
Yeah, good. It's not, right? We can't ever have e to the x being 0. There's a few reasons. So this has no solution. One way to think of it is thinking about the graph of e to the x. This graph always lives above the x-axis, right? E to the x is always greater than 0, never equal to 0. Oh, I can't read that. Never. Sorry, I got some weird lighting conditions. Another way to think of this is if you take the natural log on both sides, you'd get the ln of e to the x equals the ln of 0, i.e. x equals the ln of 0. But the ln of 0 is undefined. Remember, the natural log function has a vertical asymptote at x equals 0. This number does not exist. This is not a real number. So we get nothing from e to the x equals 0. And usually I think people think of it like this. E to the x is always positive, never equal to 0. So the only two solutions to this equation are 0 and -3. I have one more problem like this to share with you, and then we will be done for the day. I'd like to solve the equation e to the 2x minus e to the x minus 6 is equal to 0. And this is kind of similar in spirit to the problem we just solved. But in mechanics, it's slightly different, right? There are no common factors I can pull out here. But I would still like to factor this. And the trick to factoring an expression like this is to realize or remember that e to the 2x is the same as e to the x squared, right? A to the x all to the y is the same as a to the x times y. So this is e to the x all squared minus e to the x minus 6 equals 0. So secretly, this equation is quadratic. It's not quadratic in terms of the variable x. It's quadratic in terms of e to the x, right? Like if I cover these up, this is some stuff squared minus that stuff minus 6 equals 0. This is quadratic in the variable u equals e to the x. And some people like to factor it straight from here. If that's you, that's great. Other people like to explicitly write down this substitution, write it as u squared minus u minus 6 equals 0, and then factor it like this. Either one is fine. Whatever you prefer is fine. U squared minus u minus 6, if I factor that as a normal quadratic, that is u minus 3 times u plus 2. So we have that equals 0. Which means, I plug back in, this means e to the x minus 3 times e to the x plus 2 must be equal to 0. The first one tells me e to the x has to be 3. The second one tells me e to the x has to be negative 2. One of these gives me a solution. One of them does not. Which one does not give me a solution?
Second.
Yeah, the second one. This has no solutions. Because again, e to the x is always positive. Never going to be equal to negative 2. This guy, I take natural logs on both sides. The natural log of e to the x is just x. So this is x equals the natural log of 3. And that is our only solution here. All right. So these are the basic types of equations you're going to encounter in the first part of section 4.5. In the second part of section 4.5, we're going to solve equations whose variables are stuck inside of logarithms instead of equations whose variables are stuck inside exponentials. We'll be applying more or less the same logic, just kind of in the backwards way. I'll give you a quick, simple example. So next time, what we'll be working on, and this next time, by the way, this will be the lecture that I record and upload for you on Thursday, because again, Thursday the college is closed. We don't have class. Next time, we will look at equations like the natural log of x minus 2 is equal to 7. So my variable is stuck inside the natural log. And the trick here will be a new operation. Instead of taking logs, what we call it is exponentiating. In other words, I will put both sides into the power of something. Here we will exponentiate using the same base as the logarithm involved in the equation. We don't have a choice like we do with the exponential equations. We have to use a particular base exponential because I need the left-hand side to clean up very nicely. So e raised to the natural log of x minus 2 is just x minus 2. E raised to the 7 is just e to the 7. We leave it like that. So here what I would get is x equals e to the 7 plus 2. These are called logarithmic equations, equations where your variable is stuck inside of a logarithm. They can be a little bit cattywampus for a few reasons. The logarithm, remember, has some domain sensitivity issues. You cannot plug a negative number into a logarithm. So if, for example, I did a bunch of work and got x equals 0 out, then the original equation would be really unhappy because when I plug 0 in here, I would get the ln of -2, which is undefined. So we'll have to be on the lookout for that sort of stuff. The other thing we have to do is from time to time, use some of those properties of logarithms. You know, maybe I have multiple logarithms on one side here with variable stuff inside, and you'll have to combine those into a single log before you can exponentiate. But I think we've piled enough on for today that I don't want to dig any deeper into this section. I want to stop here so that you guys have a chance to work on the homework problems that are up. It's a somewhat long homework set, has all of 4.4 on the log laws and half of 4.5, the exponential equations. Please do work on that between now and Thursday. on Thursday, I will upload that recorded video lecture for the second half of 4.5. I will also be posting another homework set, which will be due on Thursday of next week, a quiz, which will be due on Thursday of next week. And then remember, of course, that the exam is Thursday of next week. So we're moving through here quickly. 1 week from this Thursday, next Thursday, the 18th, will be your third midterm exam. And then we're going to scurry after that as quickly as we can through the algebra of matrices. If I have to sacrifice some of the conic material or sequences material at the end of the semester in order to give you a good treatment of matrices, I will, because that stuff is more important. And your professors in later classes will assume that you understand how to deal with matrices and systems of equations. They're less likely to assume that you know how to deal with sequences and series. But we're gonna nail all that stuff. The conics might get squished out, and if that happens, that's okay. It really doesn't hurt you anywhere in the calculus sequence. But I will make sure to post some supplemental material, so anybody who wants to read, learn, or watch videos about those can. But that's where we're going. All right. That's it from me, guys. I hope you have a lovely rest of your day. If you need anything from me, remember you can come by office hours, send me a Canvas message or an email, or you can post to the Discord. Otherwise, I will see you a week from today. Take care.